Hi guys, welcome to lab session 2 for COSC210 database management systems. Today we're just going to continue running through some of our SQL commands. So before we get started, we've got some housekeeping to do. The first thing you'll need to do is go and upload your practical number 1 database back in to a new practical number 2 database. So you can do that by using your create db command to create a new practical number 2 database. Remember to substitute in your username in place of mine so that you have your own database instead of crashing into my one or somebody else's database. And then we can log into that database, and using the \i command and putting in the path to your prac1 SQL file, you can run that SQL file and actually create all of the database tables and load all of the database data into them. So if you're having difficulties creating the SQL file from practical number 1, just jump back in. It's the final step from prac1 where you'll be using the pg dump utility to output that database, a named database, into an SQL file, and you'll run that SQL file back in as I just described. So the end result of that should be a nice database that contains all of the data that you need. So my prac2 database is just off here over onto the left hand side, and if I do a /dt command, you can see that I've got all of my database tables there, and if I check using a select query on the employee table, oops, you can see that I've got some data in there as well. So once we've got that in place, we can then begin our prac. Now there's a couple of things that we'll cover off on before we move into today's practical exercise. The first is an introduction to 3-valued logic. Now 3-valued logic involves the use of null-valued attributes, or null values. So in SQL it's possible to have null-valued attributes, and a null value represents a piece of information that's missing. It might be simply unknown, it might be withheld from the database, or it might not be relevant to the entity that the tuple represents. And we looked at some examples of that in last week's lectures, where we were working with entity relationship diagrams. And we're actually implementing the databases from the database tables from the entity relationship diagrams. We might have attributes that aren't relevant for a particular entity type. So because a null value represents something that's unknown, 2 null values are considered to be different from one another. So null will never equal null. When null values are involved in comparison operations, the result is considered to be unknown. So we've added a third value, this unknown value, to our 3-valued logic. So this gives rise to this 3-valued logic system where we have true, false, and unknown. Now below we've got table 5.1 here to outline the values of applying null values to our and, or, and not operations. We can see that if we have an unknown value and a true value, the answer is immediately unknown. If we have unknown and a false, it's false, because for an and to return a true result, we have to have a true for both attributes. And if we have, again, if we have an unknown and an unknown, we're going to end up with an unknown result. Similar arrangement for or, only if we have at least one true, it's going to be true. If we have we have an unknown and a true, we end up with an unknown. So it's a slightly different, slightly unintuitive relationship here. So go through and review these tables so that you understand what's happening with the logical operations. Here we have the examples of those, some examples. So if we have unknown and true, the result is unknown. If we have unknown or true, the result is true. If we have not unknown, the result is still going to be unknown. It's this one here. There's no negation per se for unknown. Here we have some practical examples moving down. So in SQL, the null value can be tested for using the is and is not operator. So if we have a null value in our database, we can test for that null value using this is operator. So here we have an example where we're returning all employees who do not have supervisors. So in this situation, we're looking for null values in the super SSN field on the employee table. So we can see here we're grabbing the first name and last name from our employee table where the super SSN is null. So we've used the is null is operation there. We can return all employees who do have supervisors as well by using the not null is not null operation to check for tuples for which there is not a null value in that situation. Our nested select queries is the next topic that we're moving on to in SQL. So far our select queries have only involved really a single level, so we've only had a single condition in the where clause. And some queries require that existing values in the database be fetched and used for a comparison value. So for example, we have an example down below here where we're returning a list of all project numbers that involves an employee with the last name Smith as a manager or a co-worker. Or a worker, sorry. So in this situation, we're actually using the in operation. We're combining it with the in operation. First of all, we're performing two subqueries that we've nested within the where clause of our top level subquery. The first query returns the project number of all projects for which Smith is actually a manager. The second query returns all of the project numbers for which Smith is an employee, and you can see that we've used the manager SSN in the first query and the employee SSN in the second query. And we've put those two subqueries together with an OR operation, and we've used the in operation here to return the project numbers such that they're in either of those situations. So if the nested query only returns a single tuple with a single attribute, then the result will be a scalar. So what we mean by scalar is it'll be a single value. It won't be an array of values or a set of values. And in this situation, you can use it for a direct comparison with an equality operator or even another comparison operator with the outer query. Sets can also be compared. Here we have a query where we're grabbing distinct employee numbers from the works on table, where these two values are in this particular subquery from that. So we're selecting the hours for that employee. So we're comparing sets to each other in this situation using the in operator. The all operator can be used to compare a single value or a multi-set of values returned from a nested query. So here we're returning all employees with a salary greater than all employees in Department 5. So we starting at the bottom again, we have a nested query where we select the salary of all employees from Department 5. Then we have our salary comparing to with the greater than comparing to all using the all operator. So we're comparing all tuples from this subquery with the salary attribute of all tuples in the employee entry here. So when dealing with nested queries, it's possible to have ambiguity within the parameter names between the outer and the nested queries. What we mean by ambiguity is we might necessarily know which version of an attribute will be referenced by which query. So if we have two tables the same, we can't be sure which attribute, which version of that attribute, which table's attribute is being referenced. To get around that, to remove the ambiguity, we need to qualify the names with an alias. And we can do that by applying the as operator. So it's very similar to the rename operator in relational algebra. Here, only it works on relations and not attributes. So here we can see we've got a select query. We're selecting from our employee table, but we're using this as operator to rename this instance of the employee table as E. We can then use this alias to refer to particular attributes. So you can see that in the first line of the select query, we're actually referring to the first and last name by qualifying it with this E. So we've got E.firstname, E.lastname. So we're explicitly stating we're grabbing the first name and the last name from the table aliased as E. We're following on down in the subquery. We've specified that the dependent table will be known as D using the as operator. And again, we've fully qualified all of our attribute names in the subquery by using the E and D aliases followed by the dot operator. So whenever you're working with multiple nested queries, it's always a good idea to alias each individual table so that if you do happen to use the same table twice, you can be very clear and explicit about which instance, whether it be the outer instance or the inner instance, that you're grabbing your attributes from. So be careful with that one, and it's always good practice to use this notation to alias your tables. The final section that we're looking at today actually looks at the exists uniques clauses, and we're also looking at some table joins as well. So we'll move through, first of all, to look at the exists function. So the exists function in SQL is used to check whether the result of a correlated nested query is empty. Now that's a little bit of a mouthful, but what we mean by a correlated nested query is that we're using instances or tuples from the outside query as part of the inside one, the nested query. So in this particular situation below here, we're selecting from the employee table, and we've renamed that table as E, and we're dropping references to E into the subquery below. So you can see we've got the E serial number, social security number, sex and first name, all referenced in the subquery, and we're comparing that against attributes from the dependent net table that we've named as D. So we refer to this as a correlated query because the employee references in the subquery are linked to the outer query directly through the use of that alias. Now, the result of the exists function is the Boolean value true if the nested query contains at least one tuple. So by combining the exists clause with a correlated query, we can test the subquery for every tuple in the outside query's table. So for example, here we're going through, and for every employee record, we're selecting the dependents from the dependent table, and we're being sure to link in and correlate our query by ensuring that the dependent's employee serial social security number is linked up with the employee social security number, and so forth. In this particular situation, we're returning all. We're also correlating the gender. So if we're correlating the gender and the first name and last name. So we're first name. Sorry. So we're grabbing dependents. We're selecting employees that have a dependent that has the same gender and first name as the employee. So it's a little bit of a tricky query, but it's a nice example of a correlated query that uses the exist clause. So we're testing each employee record against this condition, and if there's any tuples returned that match this query here, so if this subquery isn't empty, this will return true, and we'll end up returning the first name and last name for that particular tuple in the employee table. We can combine that with the not operator. So here we've got an example where we're retrieving the names of employees who do not have dependents. So again, we're going through. This is another example of a correlated query, only in this situation we haven't used aliases to give our relations a new name. So we've just used the employee and dependent tables. Now it's fine in this situation because there's no ambiguity. The employee table, there's only one instance of that in this whole query, and it's in the outside table. The dependent table, there's only one instance of it, and it's in the inner query. So in this situation, starting at the bottom, we're grabbing for each employee, we're grabbing the dependents, such as the employee's social security number matches the employee social security number on the dependent table. So we're correlating the two queries together, and we're using the exist clause. So if there is a dependent, that'll return true. We're then performing a not operation to negate that. So this will give us all employees who do not have any dependents by building that query up by using a correlated nested query. We can, of course, remove the negation to retrieve the names of all employees who do have dependents. So in this situation, the same scenario again, we've got a correlated nested query to grab the dependents for each employee, check for each employee that if there's any dependents in the dependent table, and if there is any single row returned from this subquery, it'll return a true for that particular tuple, and we'll end up with an employee, that employee record returned. So for example, we can try these two out. We drop this one in. You can see that we've got 6 dependents returned that do have, 6 employees returned that do have dependents, and we've got, hopefully, 34 employees returned that don't have dependents. That makes sense because we have 40 employees in total. So it's a nice little test to make sure that our subqueries are working. So in the previous examples, the nested query, if the nested query returns true, any tuples, for any tuple, returns any tuples, the exist function will return true, and it's negated by that not clause. We can extend that to name managers who have at least one dependent. So here we've got a double nested query. We start again by correlating everything together. So we've got our employee table at the top and our dependent table underneath. Now in this situation we've actually got 2 instances of the dependent table in our query, but we've divided our query up using the brackets, using our curved brackets here, and in this situation that's going to limit the scope of each of our references. So when we're talking about the manager SSN here at the bottom, oh, sorry guys, scratch that. That's actually a dependent. It's not a department, so there's no need to correlate that. So scratch what I just said. Essentially, we're searching for the department by manager SSN down the bottom, correlated against our employee, and we're searching dependent up here, correlated also against our employee. So in this situation, we're first of all grabbing managers, then we're checking using an AND clause here if they have any dependents. So we've got a double nesting situation going there. So sorry for confusing those two, but they're actually department and dependent there. So the final example that we're going to look at today is actually one of the more complicated queries that we'll see in this course. It's a universal quantification query. So we'll jump straight into the example so that you understand what we mean by that. So here we have an example where we want to retrieve the name of each employee who works on all projects by Department 4. So we only want to return employees if they work on every single department of Department 4. Not just one project, not just a couple of projects, all of the projects from Department 4. Now, to do that in relational algebra, you'll use the divide operator, and it's a really simple process, a relatively simple operation in relational algebra. But in SQL, we don't have the divide operator, so we have to nest a double not exists clause. So starting at the top of this table, we're actually selecting from our employee table, and then we have our first not exist clause. Now if we jump down into the second part of this query first, we start by grabbing the department numbers. Now we're grabbing the department numbers such that there doesn't exist a project that the employee doesn't work on. So you can see we actually end up rewriting the query in a really awkward way to implement it in SQL. So we're actually selecting the employee such that there does not exist a project controlled by Department 4 that the employee does not work on. So what we're doing is essentially we're searching for a project in Department 4 that the employee doesn't work on. That's what we're doing in this step here. So we're searching for an employee that they don't work on, and then we're searching such that that situation doesn't exist, and we end up in our outside. We end up negating that outside one to get that second negation outside the query here. So if we drop this one in to our SQL table, you'll see that it actually returns 2 people. So there's 2 employees that actually work on all projects by department number 4. So what's happening in this query is for each employee, it's picking out an employee record, then it goes down, it selects department number 4, it grabs, then it performs the second part of the query. It checks to find an employee, a record, a project for department number 4 the employee doesn't work on, and then you end up with the double not exist unfolding back up through your query to return that one. So it's slightly more cumbersome, but it does nonetheless return the correct result, and it'll give us employees that work on all of department number 4. So in your own time, you can pull that query apart and go through it step by step. So for example, we might start by grabbing department number 4. We'll go through this one briefly. You can see that there are 2 projects worked on by department number 4. So we want to get employees that work on both projects 10 and 30. The next step is that we go through and we get projects. We try to find a project that exists, a project in department number 4 that exists that the employee doesn't work on, and that's going to wipe out most of our employees. And then we go back through, and that'll return those ones, and we want to find situations such that doesn't exist. So a slightly more complex query, but go through and have a look at that one in your own time. Final section in today's video looks at table joins. Now, table joins can be implemented simply by using the equivalence operation between our foreign key and primary key, or the foreign key and the referenced key from the referenced table. So we can see here in a couple of examples, we can either, or we can use the join operation as well. So we can start here. We can join employee to department on department number. We've also got an extra filter in here. Or we don't even need to use the join operation. We can just go select from employee and department where D number equals DNO. So the from clause the from clause results in a single joined table. So essentially we glue these tables together. Then we glue the tables together according to this condition, and then we retrieve all of our results from that according to that joined table. So we apply any filters we have, and then we return any results from that. We can perform outer joins. So recall an outer join, an inner join will only return tuples for which both tables participate in. Sometimes we might want tuples returned from one table even if they don't have a corresponding record in the other table. And in order to do this, we have to use an outer join, and we can use a left outer join in the example. So if we wanted to grab all employees and their supervisors, including those without a supervisor, we would have to use a left outer join because we want to get employees that don't necessarily participate in the supervisor relationship in that situation. So the left join indicates that the relation on the left of the expression should have all of the tuples included. Null values are returned for ones that aren't linked. So if we throw this example into our table here, you can see that there's actually a bunch of employees that don't have a supervisor, and that indicates that they're basically bosses or directors that just don't have anyone supervising them. So if we were to use a standard join, these records wouldn't be returned as part of the result set because they only have one table participating in them. They're not linked back to the employee table via the supervisor relationship. So they'd be left out if we used an inner join. But because we've got a left outer join, those items have been returned, and we've got null values in the supervisor field here. So that ends our look at SQL for now, and you've got some exercise to go through and do, so make sure you run through those and have a look at the solution. So thanks for listening, guys.